Okay, we are finally almost done with Unit 6. This is the last part. For this, we're going to look specifically at nuclear energy. We're going to talk about what is radioactivity. What are the forms of radiation given off because of nuclear energy? What is nuclear half-life? How to calculate nuclear half-life? As well as looking into what is fission and fusion. So let's begin. What makes things radioactive? Well, when things are radioactive, it's because there is an unstable nucleus of an atom. There are certain isotopes, which isotopes were talked about way back at the beginning of first semester. Elements that have the same number of protons, which means the same element but different number of neutrons, different masses. Anyways, these have an unstable nucleus, often because they have way too many neutrons. So when you have an unstable nucleus, you are radioactive. When an atom is radioactive, it undergoes decay, which happens is one element will turn into several totally different elements because the number of protons changes. So, for example, uranium can turn into barium and krypton, and then this can decay and create some other elements. The kind of decay that occurs determines on what kind of elements are created. In this class, we are not going to go into the different, specifically what are called nuclear reaction equations. You just understand that when you have nuclear decay, things are radioactive because of an unstable nucleus. And when it does give off decay, it will give off the following: either alpha, beta, or, move this, gamma radiation. So these are the three forms of radiation given off due to nuclear decay. Alpha particles are the weakest particles, beta's kind of in the middle, and gamma rays are not even particles, they're pure energy. It's an electromagnetic wave. It's the highest form of electromagnetic waves. In the next unit, Unit 7, we'll talk about the electromagnetic spectrum, and you'll learn that gamma rays are the strongest form on the electromagnetic spectrum. So again, when you have an unstable nucleus, you have radioactivity. That element decays, creates new elements, and as part of the decaying, it gives off radiation, either alpha, the weakest, beta, and or gamma. It can give off all three or just one of them. Next, the rate of nuclear decay. How often do things become radioactive? Well, I mean, they're always radioactive, but how long does it take for the element to decay into something else? This is the idea of half-life. Half-life is the time required for 1/2 of a sample of radioactive element to decay. So what happens is, let's just, easy number. Let's say we start with 100 grams of something. And let's say it has a half-life of 1 day. So after 1 day, half the 100 grams will be gone. It will decay into something totally different. Let's pick an element just to make it easier to understand. Let's just say carbon. So let's say I have 100 grams of carbon. After 1 day, and it has to have a half-life of 1 day. After 1 day, half of it will turn into a different element. So how much carbon am I left with? Well, I'm left with half. So I'm left with 50 grams. Now, the biggest misconception is it's 50 grams every time. No. Half-life is half of that sample. So after the first day, half of 100, which is 50, is left over. Now, on the second day, half of this will decay into something else. So half of 50 is 25 grams of carbon. On the third day, half of this will decay into something else. So how much carbon's left? 12.5 grams. On the fourth day, half of the 12.5 will decay. So how much is left? 6.25 grams. And so on and so on and so on. So half-life is, it takes half of whatever is left over each time. So it's always half of this, then half of that, half of this, half of that. It's not the same, it is not the same amount every time. It is not always 50 grams. It's not always whatever number. It's always half of the sample. Hence, half-life. Wow, mind blown. The half-life of different isotopes vary. So carbon-13 has a different half-life than carbon-14. However, the half-life of the same isotope is always constant. So, for example, since I said carbon-14, let me move this to the side. We're not going to watch the Tyler video. Carbon-14 has a half-life of 5,730 years. It takes 5,730 years for half of a sample of carbon-14 to decay into something else. But, I mean, again, every isotope is different. Uranium-238, it takes 4.5 billion years for that to decay, for half of that sample to decay. But Erdium-182, it takes every 15 minutes. So, let's look at a sample problem that you might have. Here's a question that says, after 45 minutes, how much erdium will remain in a given sample? And you're going, wait a minute, you didn't tell me how much I started with. Well, this is just asking of, let's pretend you had any amount. How much would be left over? About, what fraction amount? So ask yourself the following. How many decays happened in 45 minutes? Well, if Erdium-182 decays every 15 minutes, in 45 minutes, it means it decayed 3 times. It decayed after 15 minutes, 30 minutes, and then 45 minutes. So it decayed 3 times. So it took half of a sample, then half of the sample, and then half of a sample. How do you do that mathematically, though? The biggest mistake is people think, oh, it's a half plus a half plus a half. Well, 0.5 plus 0.5 plus 0.5 is 1.5. That doesn't make any sense, because that means you created more than what you started with. What you do is you multiply. So you say you have half a sample that decayed. You multiply that by the next half of a sample. And in case you don't remember how to multiply fractions, you multiply the numerator and you multiply the denominator. So it would be 1 times 1, which is 1. 2 times 2, which is 4. So 1 over 4. And then, again, there's another half-life, because we said there's 3 of them, times another half. So 1 times 1 times 1, which is 1. 2 times 2, which is 4, times 2 is 8. So after 45 minutes, how much erdium will remain in a given sample? 1/8 of however much there originally was. Whatever there originally was. So let's pretend it was 100 grams. So you start with 100 grams, then it went to 50 grams, then 25 grams, and then 12.5 grams. So 1, 2, 3. And if you did this, if you actually put this in a calculator, 12.5 divided by 100 is equal to 1/8. It's 1/8. This is 1/8 of the original amount. So it kind of just shows you another way of solving it. We'll do a lot of half-life questions in class. This is just, again, giving you a general overview of what half-life is. It takes the amount of time for half a sample of an isotope to decay into something else. The next stuff is really this stuff's super easy. Types of nuclear reactions. It's just what's the difference between nuclear fission and nuclear fusion. So what is nuclear fission? Fission, let me move this up here. See if I can find a spot real quick down here. Fission is the process of splitting an atom. When you do fission, you're taking a very large nucleus and you're splitting it into different elements. So again, it's a process of splitting a nucleus into several smaller nuclei, meaning it creates smaller elements. You take a very big, heavy element, and then you create smaller, different elements. Nuclear fission is used in atomic bombs. It's used at nuclear power plants, which creates electricity. This goes back when we talked about conservation of energy, how nuclear rods, boils water, creates thermal energy. Those nuclear rods are having nuclear fission. Those rods are radioactive. To figure out how much energy is produced, that's where Einstein's equation E equals mc squared comes in. So as long as we know the mass of that object, we can multiply that by the speed of light squared, and that can tell us how much energy is released. So, for example, if you have, 50 kilograms of uranium or plutonium or whatever it is to make an atomic bomb, you can calculate how much energy that atomic bomb will give off. So again, fission, splitting an atom. This one I think is easier to remember. fusion. Maybe I know why it's easier because I have this stupid analogy, which I'll talk about in a second. But fusion, when you fuse things together, it's the process of two smaller elements combining to create a larger element. The only place this is typically found in nature is the sun. Because in order for nuclear fusion to occur, there has to be tremendous, extreme, and I do mean extreme amounts of heat. The only place we found that is in stars. For example, the sun. So the reason why the sun works is because it takes hydrogen atoms and it fuses them together to create helium atoms. Now, what's interesting is nuclear fusion produces way more energy than nuclear fission. But the problem, and it's way, not easier, in fact, it's way harder, but it's way less dangerous in terms of waste products. In fact, if we were able to figure out how to do what's called cold fusion, which many say is impossible, that means we can do fusion at, I don't want to say reasonable temperatures, really high temperatures, but temperatures we can produce here on Earth. One glass of water can theoretically has enough hydrogen in that glass of water to give everyone in Cincinnati electricity for over 100 years. One glass of water. Now, I'm just making that up, the number, but it is an extreme amount of years that one glass of water can give. Basically, it would mean that electricity would be almost worthless. When I say that, I mean is your parents' electric bill, when you go over your electric bill, will be basically pennies a year. Pennies. Versus some people easily have over $100. Some people have over $300 a month. A month. And I'm saying you can get electricity for pennies a year if we figured out how to make fusion here on Earth. Fusion produces way more energy than fission. But again, the problem is you need something as hot as the sun to produce this reaction. Now, we actually have created nuclear fusion reactions here on Earth, but the amount of energy it takes to do it exceeds the amount of energy given off. So it actually takes more energy to do it than energy we get back, which is why it's not practical yet. But if we can figure out a way to make it practical, history will be changed forever. So again, fusion. You take two smaller elements and you fuse them together. Now, I always remember this because, I don't know if you can see these guys. This is Goten and Trunks. I really like Dragon Ball Z. Dragon Ball Super now is the new show. But they do the fusion dance and they fuse together. So I always say, if you remember one, you automatically remember the other. So if you can just remember that fusion means to come together, then fission has to mean the opposite. So if fusion means to come together, to fuse together, then fission has to be to come apart, to split. So there you go. Again, fission and fusion, very, 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 very basic. To wrap up for this part, what just happened there? Fusion is when nuclear fusion fuses atomic nuclei together, so two hydrogens will create helium. Whereas fission is what happens when you split an element into different elements. And then that big element split into smaller elements, which splits into smaller elements, so on, so on, so on. So there you go. Fission and fusion. Radioactivity, unstable nucleus, gives off alpha, beta, gamma radiation. And then we talk about nuclear half-life, the time it takes for a half of a sample to decay into something else. We are done with Unit 6. Yes!